Good morning, class. So I just want to continue talking about um, velocity and time and our problems associated with these things. Okay, so let me present. Okay, so we've spoken about our situations, right? We've spoken about having situations where we have constant velocity or situations where we have constantly changing velocity. And then also situations where we don't know if the velocity is constant or constantly changing. Um, but as we go forward, we're going to be focusing much more on the two situations where the velocity is constant or constantly changing. All right, and we're just going to assume everything is going on in a straight line here. And and the first thing we want to talk about today is that we've spoken about the situation where our velocity is constant over time. That's what we see here, right? Our velocity is rock solid constant. Right? So let's say we're cruising down the road at 10 meters per second and it's constant. Well, what does that suggest? It suggests that we're covering 10 meters of distance every second. So after 1 second, we would have covered 10 meters of distance. After 2 seconds, 20 meters of distance. After 3 seconds, 30 meters of distance, and so forth. And as you might think, that would look very linear, right? At 0 seconds, I would have covered 0 meters of distance. After 1 second, I would have covered 10 meters of distance. After 2 seconds, I would have covered 20 meters of distance. After 3 seconds, I would have covered 30 meters of distance, and so forth, or 30 meters of displacement if we were talking about it as a vector. So we're just cruising down the road in a straight line at a constant speed. What is that going to suggest for our position or our displacement? That it is going up linearly. Okay, so when an object is traveling at a constant velocity, a plot of position versus time will give us a straight line graph. Okay, that's what we just said here. So since our distance, our displacement is going up consistently 10 meters every single second, we're going to get a linear plot of the total distance we have traveled versus time, or our total displacement versus time. Okay, the slope of this graph is the velocity of the object. So the slope, if we took any 2 points and we said, what is our rise over run, right? What is slope is rise over run, right? So if I said, what is my rise? Well, from 2 seconds to 3 seconds, my rise was 10 meters of distance, and my time, sorry, my time was 1 second. So what would my slope be? Slope would be rise over run. 10 meters of distance over 1 second of time between any 2 points, right? Would be my speed, 10 meters per second. Okay, that would be my speed, my velocity. And I could do it between any 2 points, right? If I took this point and this point, what's my rise? My rise would be in 3 seconds. I rose 30 meters in 3 seconds. So my velocity would be 30 meters of rise in 3 seconds, which would simplify to 10 meters per second. So we'd say, so the conclusion is the slope of a displacement versus time graph is equal to the velocity of the object. Okay, so the slope of a position versus time graph is equal to the velocity of the object. All right. And the velocity versus time graph for an object with constant velocity is a straight horizontal line, which we've spoken about already, right? So if we're looking at velocity versus time, if we're cruising along at a constant speed, well, it's just going to be a horizontal line on a velocity versus time graph. So obviously, these two graphs kind of describe the same motion. It's just different. What we're graphing is just different. Here we're graphing velocity, and we're saying the velocity is unchanging, it is constant. And over here we're saying, well, how about our position or our displacement? Well, that's going to be changing linearly because I am moving along at a constant speed. Okay, so you want to we want to be able to make the association between what a velocity versus time graph is going to look like and what the corresponding position versus time graph is going to look like. Okay, and just to clarify, just to continue a little bit, so what we just spoke about was having a positive velocity. If we're cruising along at a positive velocity, let's say 10 meters per second, well, we said our position is just going to keep going up by 10 every second, plus 10, plus 10 meters, and 20 meters, and so forth, right? So our position is going to change linearly as long as our velocity is constant. Well, what if we had a negative velocity? All negative velocity means, as we've said before, is the direction of the velocity. So all this graph is suggesting is that let's say we had a negative 5 meter per second velocity. All that means is we're traveling in the negative direction at 5 meters per second. So imagine a straight road. Okay, so if we're and there's some position that we're going to call 0. We just arbitrarily pick some location on the road to be location 0, and these are positive locations, and these are negative locations. Okay, -1 meter, -2 meters, let's say, and so forth. And so if we're cruising along at -5 meters per second, all it means is we're cruising along at 5 meters per second in the negative direction. Okay. And what that's going to do to our slope is make it negative. So this might suggest we started at some positive location. Okay? On a displacement versus time graph, this would be a displacement of 0. So we started off at some positive displacement. Let's say we started off at, I don't know, let's just say 20 meters of positive displacement. That would mean we're over here at 20 meters. Here, let me see if I can. Let me change my scale just to make it simpler. I'm going to make each of these worth 5 meters. So this would be positive 5 meters, positive 10 meters, positive 15 meters, positive 20 meters. Okay, so we're starting off at this location, at the positive 20 meter location, or at least that's when we're beginning to observe the object at least. And these are negative locations. And this is just arbitrary. We just, along the road, we declare some location to be 0. We declare some locations to be positive to the right of that location, and some locations to be negative to the left of that location. And if we have a negative velocity, it simply means we're traveling in the negative direction. So in this case, we might say I started out at this 20 meter location, and every second I'm traveling 5 meters in the negative direction. So 1 second later, I would be here. And then 2 seconds later, I would be here, and 3 seconds later, I would be here, and after 4 seconds, I would be here, and after 5 seconds, I would be here, and so forth. So after 1 second, I would have moved 5 meters in the negative direction, so I would be at the 15 meter position. I'd be over here at 15, and another second later, I would be at the 10 meter position, so I would be at 10, be over here. And then 1 second later, I'd be at 5. I'd be over here, right? And then 1 second later, I'd be at 0. I'd be over here. And we would linearly, it would show a straight line, linear slope, but it would be a negative slope, okay? It would be a downward sloping line because we're traveling in the negative direction. That's all. Okay, so nothing crazy about it, but you do have to get used to being able to see things like negative velocity and say, what's a negative speed? Well, it just means we're moving in the negative direction. And what's a downward slope on a velocity graph, or on a displacement graph rather? It just means we're moving not in the positive direction, but we're obviously moving in the negative direction. If we're moving from a location of positive 20 meters to a location of positive 15 meters to a location of positive 10 to positive 5. We're moving from positive 15 to positive 20 to positive 15 to positive 10 to positive 5. We're moving in the negative direction. Okay? So again, constant velocity, linear shape, as expected, as seems logical. Okay. So again, you just want to make this association between constant positive velocity means our displacement is going up. And it really depends where we started. If we start, we could declare some location on a straight line to be location 0. And let's say we start here at location 0 and we have some positive velocity. Let's say our positive velocity is 3 meters per second. Well, we'd say I'm starting at 0 and starting at 0 and each second that goes by, 1, 2, 3, 4, I go up by 3 meters. I go up by 3 meters, up another 3 meters, up another 3 meters, up another 3 meters. And so my displacement versus time graph would look like it has a positive linear slope. What would happen if I moved at a constant velocity of positive 3 meters per second, but I started instead at, say I started my observing here at the positive 2 meter location. So I'm moving in the positive direction at 3 meters per second, and we're starting observing the object at this location. Well, you'd say, well, I started at time 0, it was already at the 2 meter location, and each second that went by, it moved to the right, moved in the positive direction by 3 meters. So it went up 3 meters, up another 3 meters, up another 3 meters, up another 3 meters. It would simply look like that. So if you're moving in the positive direction, you should see a positive slope to your displacement versus time graph. All right? If, on the other hand, we had a negative, so think of this as a different object, we're moving it with a negative velocity, let's say negative 1 meter per second. Keep it. There we go. And let's say we started at 0. Okay, so let's say we start at the 0 location. So now we're moving after 1 second. We're over here at the negative 1 meter location. After 2 seconds, we're over here at the negative 2 meter position, right? And so our slope would be negative 1 meters. After 1 second, negative 2 meters. After 2 seconds, negative 3 meters would be our position, right? And the negative is really just an indication of to the left. Okay, so we would have if we have a negative velocity, we would have a downward slope or a negative slope to our displacement versus time graph. Okay, so the point is don't freak out if you see a negative displacement or a negative velocity. It simply means to the left. And second point, if we're moving along at a constant velocity, these displacement versus time graphs should be linear. It should be straight lines. All right, next point now. What happens if we're not moving at a constant velocity? Let's talk about our second situation where we're steadily getting faster. We're uniformly getting faster, or we're uniformly getting slower. Okay, so we're either gradually getting faster or gradually getting slower. What is displacement versus time going to look like? Well, if I'm at some speed, let's say 3 meters per second, well, in the next second, or we're going to be traveling approximately 3 meters of distance, right? Approximately. But later on, let's say we're up here and we're going faster and we're traveling at maybe 5 meters per second. Well, in the next second, we're going to travel a larger distance than we did at the beginning. We're going to cover 5 meters of distance, a little bit more than that because we're actually speeding up the whole time that we're moving. So as time goes by, because we're getting faster and faster and faster, we're covering more and more distance. So in the first couple of seconds, when we're traveling, let's say 3, 4, 5 meters per second, we're going to cover a certain amount of distance. But later on, when we're traveling 7, 8, 9 meters per second, we're going to be covering a larger amount of distance in each second because we're going faster. So our displacement versus time is not going to be linear. So let's say we started off at the 0 location. So we're starting off here, let's just say. So our displacement would be at 0. What is going to happen, though, is you're not going to get a linear graph. It's going to be, figure out how to turn whatever is turned on off. Okay, it's going to be gradual, but then it's going to slope upward. So you're going to get a non-linear displacement versus time graph. You're going to cover a certain amount of distance relatively small amount of distance in the beginning, but later on when you're going faster, in 1 second, you'll be covering a larger amount of distance. So you're going to have this nonlinear displacement versus time graph. Okay? So that is an important thing, that you make that connection between those two. Let's see if I can just pause this for a second.